let us open a file which is basically let's say this one. Okay, so we are talking about the magnetization of paramagnetic substance quantum mechanically, and we had gone through the entire calculation, and eventually we obtained the magnetic susceptibility, which turned out to be actually the normal expression was well, it was the magnetic moment that was n mu bjx, and x is proportional to h, the magnetic field. So when h is pretty large, that is magnetic field is very large, obviously you would expect that the magnetic moments to align along the field direction, and therefore total magnetic moment should be n times number of moments times moment of each one, that n mu, and that is the complete magnetization expected at large external magnetic field. Now consider the situation when the temperature is pretty large and the field is low. If temperature is pretty large and field is low, that means actually you are trying to agitate the because temperature is large, you are trying to agitate the moments compared to the magnetic field energy. And in that situation, your x, which is probably mu h by kbt, kbt is large and therefore x is pretty small, it is very less than 1. In that case, if you expand this function bj, then eventually you obtained 1 plus 1 by j times x by 3, which is 1/3 of 1 plus 1 by jx. And again, you see that when j is pretty large, I explained physically, and also some of you came up with the argument that when j is pretty large, then there are lots of orientations between 0 to pi for the magnetic moments, and therefore as if it will appear to be a continuous possible angles that is making with the magnetic field, and therefore it should approach the classical limit, and that is what it does. When j tends to infinity, it becomes x by 3. If you put x, whatever you assumed x to be like this, then if you put it back here, x by 3 in case of this one, then it will be basically okay, at j infinity, then it becomes 1 by j is 0. So n0 mu square by 3 kt, that is the susceptibility, and that is what is the Curie paramagnetic susceptibility as you obtain in case of classical system. And otherwise, for high temperature, large temperature, and low magnetic field, J does play some role in dictating the value of the susceptibility. Of course, I mean, this portion would be kind of constant. However, it goes as inversely proportional to T, which again does, which again does, mm, which again does agree with the experimental result as we have seen earlier, right? And this is the same thing as I said in the last class, that Bjx should approach the classical value Langevin function, Boolean function should approach the Langevin function when z is pretty large, and for obvious physical reason that we have already explained. I'm not going to explain it again. Here you have plotted, you see how it varies with h by t, the mu z by mu b. Mu b is constant, of course, it's the Bode magneton. In the unit of Bode magneton, you count the average magnetic moment, the component of the magnetic moment along the z direction on the average for particle in the units of mu b, and then you have plotted for different values of j's and so on, and it does, does agree with the experimental results, because these you see that the dots and all these point data points are the points for some kind of particular specific material for which this j, they have the state j equals to 3 by 2 g equals to 2, there's j 5 by 2 g equals to 2, this 1 by 2 and g equals to 2. So these are the states for these systems, and they do agree with the experimental results. Okay, so um, so yeah, just hold on a minute. Okay, so that is what I have written here. Look at the figure where the theoretical and experimental results agree very well. Okay, and now let me go to the so so this is what I mean. We are pretty satisfied with the theory that we have, using the canonical ensemble, using the statistical mechanics. We came up with the expression for the susceptibility, magnetic susceptibility, paramagnetic susceptibility for the systems, and we obtained the general formula for the susceptibility, and we applied it. We tried to examine whether the kind of understanding that we have, and the result we obtain based on our understanding, whether that result does agree or does explain the theoretical results. And it does so for some samples whose states J values are given by this, and these J's are calculated about, looking at how about its valencies and in which orbit it is, the electrons are moving. Depending on all these things, we get the J values, and G, of course, for the electrons, G, we are talking about the electrons, so G always will be 2. Okay. So again, somebody is knocking the door. Is it? Yes. Okay. So far it is okay, and now we come to again a thermodynamics of magnetic system, but a new concept emerges from a simple system. The system we are going to talk about has a upper bound of its energy. That means, for example, if you talk about the classical gas system of classical gas, then you increase the energy, you provide more and more energy to the system. The system will go to the higher state, higher energy state, higher energy state, and it will be never bound, right? As you keep on increasing, providing energy or raise temperature, provide energy, of course it will raise temperature, and if you raise more and more, provide more and more energy to the system will be more disordered, more and more disordered, and it will just open up its more possible configurations, and therefore its entropy will be ever increasing. It will never stop. It will keep on increasing its entropy, because it will never reach the equilibrium, because you are just providing the energy continuously. However, if you have systems where the system is bound, it has the upper bound of the energy or the state. The system can only be accommodated in some kind of strict or fixed states, or the upper state that is bound, that if you provide even more energy, then it will not go to any other higher states, because no other states are available to the system. And in such cases where your upper, as far as levels are concerned, the system, the states are concerned, if it has the upper bound of the state, higher state, then the system can show something which is called negative temperature. Negative temperature, we could never realize the negative temperature, right? We do not, so far we never heard about negative temperature. Did any of you hear about negative temperature earlier? Did you hear about negative temperature earlier?
No, sir.
So how about the others? I mean, others are tongues are fixed. I mean, they cannot move the tongue. The vibration cannot be generated by you. That some sounds come out. Yes or no?
No, sir.
Cannot be. Then how? I'm shouting like I'm asking whether you have heard about this negative temperature or not. You can't say yes or no. Just only there is only Mosumi that she has to speak all the time. How about you
No,
guys?
sir.
No, sir. No, sir.
So please keep it in mind, okay? Try to interact, try to respond when I'm asking something, because I want to know whether you have heard it or not. Okay? So it apparently says, Mosumi says that she did not, come across such a thing. Certainly, I mean, as far as my knowledge goes, that probably it will appear to be absurd. The negative temperature would appear to be kind of absurd that you cannot think of. However, as far as definition of temperature is concerned, the way we theoretically define temperature, then we'll see in a moment that negative temperature, you have to name some temperature as negative temperature. Okay. So for that, let us consider a system which is mostly, mostly the questions that come in your comparative examinations, only they mostly talk about this kind of systems, two-level systems, three-level systems, and so on. So when you are talking about the two-level system, that means it has two levels. The system could be in either in the first level or second level, or it could be combination of first level and second level, right? So these are the things, but it cannot go beyond that second level, even if you energy increase the energy. Okay, so that is the concept here, that suppose you consider a system of dipoles with j equals to half. Each dipole then has a choice of two orientations. You know that if j is half, you have the states half half or half minus half. That means either up state or down state, whatever way you designate them. Because when I say up and down, this is kind of my thinking of representation. Okay, or in quantum, in terms of quantum numbers, you can say half half or half minus half, and sometimes you can say this is up, this is down, like that. Anyway, so two states are possible. Dipoles then has a choice of two orientations and corresponding energies. Minus mu dot h is the energy. If it is you know plus half, then it is minus mu h is the energy. If it is minus half, then it is minus mu dot h. So it should be plus mu h energy in presence of a magnetic field h, right? Now let us call these energies as minus epsilon. So mu h is denoted as epsilon, and therefore this energy is minus epsilon. The other energy is plus epsilon. Therefore, these are the two energies are possible for the system. Okay, for a particle, for a system of dipole with j equals to half. Okay, it will be plus half or minus half. So for a single particle, or single dipole, these are the two possible energies. One is minus epsilon and another plus epsilon. Then the partition function, at this moment you must know how to write the partition function for a single particle. That should be sum over it is minus beta En, and En basically 2 E1 and E2, because there are two levels, is a minus beta E1 plus is a minus beta E2, which is e to the power, this should be beta epsilon, and e to the power, this should be minus beta epsilon. And for n particles, certainly it should be to the power n, because if you do not you do not divide by n factorial, because you are talking about the system where the spins are fixed at some places. Okay, now then you have obtained the n particle partition function, which you can write as cosine of hyperbolic extension. I think we have done this also for a certain problem. Hence the Helmholtz free energy nkt ln to hyperbolic epsilon by kt, because k ln omega n, and s minus del a del t h, and that comes out to be like this. And the total internal energy A plus Ts, which is like this, we have already obtained earlier. M is minus del A by del H at constant temperature, and which turns out to be like this. And the specificate del U by del T at H is this. And again, the U, that U, this you write it as N epsilon is mu H, tan hyperbolic epsilon by KT, so minus N mu tan hyperbolic epsilon by KT times H equals to minus MH. Okay. So what is this? You know this M, right? This is M, this is M, and you expect it, right? So as expected, U equals to minus MH. Everything is in a very consistent manner. They are obtained in a very consistent manner. There is no ambiguity as far as the results are concerned. Now let us see how S, U, M, and C in specific heat varies. Okay, with the relevant parameter. For instance, let us concentrate. We will mainly concentrate this on this entropy. Okay, and then we will discuss later. After discussing the variation of these quantities, we'll go back to the entropy and see how the concept of negative temperature arises. Now S equals to, this is the expression we obtain, and if you plot S by Nk with respect to Kt by epsilon, then you can see the low temperature behavior. If Kt is epsilon by Kt, or Kt is very, very larger than epsilon, then you will see that epsilon by Kt is pretty small, and hence cosine of epsilon by Kt would be approximately 1, and epsilon Kt tan hyperbolic epsilon by Kt, you can just check that would tend to 0, and therefore if epsilon by Kt tends to 0, then cosine hyperbolic epsilon by Kt that tends to 1, then you will have S equals to Nk ln 2. Okay, S equals to Nk ln 2. So that would be kind of a saturation value because this is constant. Okay, so it is at large temperature because Kt is pretty large compared to epsilon. So at large temperature, the entropy will be a constant, which is Nk ln 2. Okay, all right. Now, what is the physical explanation? At large temperature, the thermal energy agitates all the dipoles to orient completely randomly. We have discussed it many times, n number of times. Each dipole can orient in 2 possible directions, and the total number of configurations is 2 to the power n, because each dipole has 2 configurations, then there are n dipoles, then total number of configurations should be 2 to the power n, right? That I think you all understand that. The 2 to the power n number of configurations, and therefore S is k ln omega, that is nk ln 2. Okay, so at large temperature, as you let the dipoles, at large temperature, you let the dipoles to orient in a random fashion. So it could be up or down, so there is no biasness on the dipoles, and therefore you have equally probable up and down states, and therefore 2 states are equally probable for each dipole, and therefore for all the n dipoles you multiply 2 into 2 into 2 up to n, so it becomes 2 to the power n for n dipoles. This is the number of configurations, and you know the connection with the entropy as is k ln omega, so nk ln 2. So this is also quite justified from this expression, that at large temperature this expression should be nk ln 2, and at low temperature we'll see that entropy will tend to 0. That also you can check from this expression. Well, having discussed about the can you do one thing? Can you check whether this behavior is reflected from this for low temperature region? Just check it once, okay? Please.
Okay, sir.
স্যার কি করতে বলেন আর একবার বলবেন, শুনতে পাইনি।
হ্যাঁ, যেটা বললাম যে লো টেম্পারেচার রিজনে আমি যেটা দেখালাম তোমাকে, এই যে লো টেম্পারেচার রিজনে যে এই যে এইটা, হ্যাঁ, এই জায়গাটা মানে এই এন্ট্রপি জিরো হচ্ছে কিনা আর কি, ইজ ইট অ্যাপ্রোচিং জিরো অ্যাট লো টেম্পারেচার, এটা কি রিফ্লেক্টেড হচ্ছে এই এক্সপ্রেশন থেকে?
ওকে স্যার।
স্যার জিরো আসছে, তাই তো?
Okay, fine, yeah. So then it is fine, okay.
Sir, Ash.
আসছে তো? Okay, all right. Okay, good. Then you see the next quantity that we are going to look at is the total energy of the system, which we have already obtained this expression. And if you plot, you see the behavior is like this, tan hyperbolic, right? And tan hyperbolic has a simple pattern like this. And certainly, say at low temperature, when the field was, field was whatever value it could be when in presence of a finite whatever small value it could be, that when t tends to 0, because this tends to 0, then you see that there is a complete magnetization which is -1, that is u is minus n epsilon, and then as temperature is raised, it goes to complete random scenario, where the average energy is becoming 0, right? And then um, um, of course, I mean, this energy is the magnetic energy. It is arising due to the magnetic moments. Okay, so don't mess up with some other energies. Now, next, okay, this is quite reasonable the way it is appearing. You can understand. And then the magnetic moment. Magnetic moment is nh n mu tan hyperbolic epsilon by kt. And if we plot like this, then we see again at zero temperature. Of course, it has the total magnetization for even a finite magnetic field. And as temperature raises, then it starts its agitation, thermal agitation, and complete randomization occurs at some temperature, large temperature, and therefore it decreases, right? And that is what we obtain here. That is also quite practical. And then the specific heat. Specific heat, let us look at it. Okay, now what is this? This is nk epsilon by kt square, and that is what the I mean expression we obtained probably earlier, that this is the expression we obtained, and then we have rewritten the expression here, this one. Then nk you are writing as delta by kt square e to the power delta by kt times 1 plus e to the power delta by kt whole to the power minus 2. So, and delta is twice epsilon. So can we write it in this form? Mm, 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 just check it out whether it can be written in this form, please.
স্যার একটু ফর্মটা আরেকবার বের করবেন, ঢোকা হয়নি।
কি বলছো?
বলছি মানে ওই যে ফর্মটা বের করতে বললেন ওটা
এই পিডিএফটা কি দেয়া নেই তো?
You write it as 1 by cos hyperbolic, right, square, and then take something common from there and try to.
হ্যাঁ স্যার এটাই আসছে।
Okay, good. So this delta is the twice epsilon, means the energy difference between the two states. So now if you look at this expression, you see this is x hyperbolic square and this is another term here, right? So these two terms will have a competitive behavior, and therefore there would be some kind of someone is raising and someone is decaying, and as a result there is a kind of competition, and as a result there will be kind of maximum here, and then it is decreasing. So the specific heat of the system is vanishingly small at low temperature, and also it is vanishingly small at high temperature, as U is constant at high temperature. For better clarity, at low temperature you need at least an energy of the order of delta to change the state of the dipole at low temperature. That is why the U is flat near t equals to 0, t equals to 0, and C is vanishingly small at low temperature. Somewhere around epsilon equals to kT or t equals to epsilon by k, it displays a maximum. Having discussed the system in detail, let us look at the same system from the combinatorial point of view. Okay, that we'll see later anyway. So now you look at it and think about it, that what it says is, what is C actually? C is I mean, why this kind of behavior? Okay, mathematically maybe kind of there is a maximum of this, because if you there's a product of two things, then could be that one is raising, one is lowering, and then at some point there will be crossing, and then other thing is dominating, decreasing, and therefore you will have this kind of maximum. But practically what is happening is that the change in energy, right, with respect to temperature. So it says that at kT by epsilon of the order of 1, I mean, when epsilon is of the order of kT, but delta, which is the energy difference between two states, so it should be actually twice epsilon actually. KT of the order of twice epsilon. Anyway, I don't have the scale here, so I cannot make it out from this scale. However, at least I can make out that the if you want to understand it physically, that at t equals to 0, as you go on increasing the temperature, the system, if it was at a lower state, at some state, say all spin down or all spin up, whatever the state is, in the lower state, I'm saying, there are two states, right? There are two states. If it was, আচ্ছা আগের দিন আমি যখন প্রেজেন্ট করছিলাম, ও আচ্ছা এটা ওখানে, okay. So when you have two states, one is the lower state, and another is the upper state, and at t equals to 0, you understand that probably all will be at the lower state. All the dipoles will try to be at the lower state or aligned in a particular direction. Of course, it would like to have a direction which is, depending on the magnetic field. Of course, it will try to align in a lower, so the total energy becomes minimum. So it will occupy the lower state. And then if you keep on increasing the temperature until and unless you go at a temperature of the order of kT or twice kT, of the order of that gap, to have a transition from one state to the another state. If the difference between two energy levels is of the order of twice epsilon, then you have to provide that amount of energy, to change the state from this to that. And therefore probably the most change in energy that would occur around this region. Otherwise there will be a small changes that will occur. There is a probability, of course, I mean, it will flip to, if there is some energy, then it has the probability to flip from one state to another. There is a probability, but the probability will be maximum at some other energy, say of the order of epsilon equals kT, and then it decreases, because after that you have nothing to do. Okay, so that could be kind of physical explanation to understand this kind of behavior in the specific heat for this system. Okay, having said that, now let me move to other document that I would open, this one. Okay, that I have already explained, this one. Now let me go to this. Okay, this is what I explained mostly. Okay, now the negative temperature concept will appear. Okay, so the same system I'm considering. There we what we talked, we remained within our realizable temperature from 0 to large, right? 0 to infinity. Say. Now let me look at the system in a different way. What is that? Now let us discuss the system from different angle. We calculate the number of ways the system of n particles in a two-level system of levels minus epsilon epsilon can be arranged such that the system corresponds to an energy E. So the system has a total energy E, and then you have to have a distribution of the dipoles between the two states. Now let us suppose that n plus particles are in the state plus epsilon and n minus particles are in the state minus epsilon. Okay, then you can write E in terms of this because your energy is n plus epsilon minus n minus epsilon, because some are positive energies, some are negative energies corresponding to two levels, and where n total number of particles is n plus plus n minus. Then n plus you can write you have two kind of equations, and then eventually you can write n plus in terms of n and E energy and the part number of particles, n minus also you can write in terms of this. Then the number of ways you distribute them, number of ways you distribute n plus particles in the up state maybe, or n minus particles in the down state. Whatever, up down it depends on energy epsilon plus epsilon minus. Okay, so then that number of ways you can distribute is of course certainly n factorial by n plus factorial n minus factorial, and that is you write in terms of n and E like this. Hence we obtain the entropy. Entropy is k ln omega, and then you just have the you just carry out the algebraic calculation here. This is all factorials, and then you can use Stirling approximation, and probably eventually you will obtain the this is the expression. Okay, then 1 by T equals to del S del E. You know the thermodynamic relation, that is you have the S, so you can carry out this derivative, and eventually if you carry out this derivation, and finally you obtain del S del E, that is this k by twice epsilon. So you can do this derivation by yourself. Okay, this is the kind of algebra, simple algebra. Just you have to keep your patience and do the steps one after another, and use Stirling approximation in this case, and then eventually we'll arrive at this. This is nothing but this is n minus and this is n plus. This is what it would. Now you see, so this is the expression. I mean, from the thermodynamic relation or definition, 1 by T is del S del E, because you know dE equals to T ds, right? That is the famous relation we know. dE equals to T ds. So 1 by T d del S. Now the concept of negative temperature is coming here. You see that as long as n minus is greater than n plus, as long as n minus is greater than n plus, then E is less than 0, because your E is, what is E? If you look at the expression for E, so this is n plus minus n minus times epsilon. Okay, so n plus minus n minus epsilon. So if n plus is less than n minus, then certainly you have E less than 0, and therefore you will have T greater than 0, right? Because n minus is larger than n plus. But if it is The other way, that is n plus is larger than n minus, then your E is greater than 0 because n plus minus n minus into epsilon is the energy, and you have ln of fraction. Ln of fraction is probably a negative number, right? Well, okay. So then T is negative. This is the, I mean, in such a situation, we name the temperature as negative temperature. Okay. So this is the kind of concept of that the concept of negative temperature is arising. If you have a situation, so it is a finite system where you have finite levels and you have an upper bound of the maximum state, maximum level. Energy wise, it has an upper bound. In that situation, you can have a negative temperature. Now let's proceed further to have better visualization, or you have to digest the negative temperature concept, and you plot this entropy with respect to energy. Now this is the zero temperature, the normal zero temperature we call, that is a zero temperature, and then if you go from there, you get positive temperatures. Generally, normally what we do, and also you have seen that entropy was 0 here, and then it was increasing and it was going to a saturation value somewhere at large temperature. This corresponds to positive infinite temperature. Positive infinite temperature means the way we realize, so far we have been realizing the temperature from 0 to infinity. That is what it is. So this is the slope. From the slope, this is S and E. From the slope is positive, and therefore temperature is positive. And the slope is decreasing, and therefore temperature is increasing, because the slope is inverse of temperature. 1 by T is the slope, del S del E. And the slope, you see, slope is decreasing, and therefore the temperature is increasing, and eventually the slope is 0, and inverse of 0 is infinity, and therefore the temperature at this point is infinity. But what is this point? At this point, what is this point? This point, at this point, your energy is 0 actually. Now, did I say that here? No. Okay. No. So what is happening? It is immediately apparent that the energy will be 0 at the energy plus or minus n epsilon. Can why the entropy will be 0 when the energy is plus n epsilon or minus n epsilon? Can any one of you tell me why the entropy has to be 0? So up to this, from this to this, you understand that entropy is increasing, the slope is decreasing, even though it is increasing, but slope is decreasing, right? It is like velocity is increasing, it is increasing, but the acceleration is decreasing. Is it that? No, not I'm confusing. Okay, let not me confuse you. So the entropy is increasing, but the slope here, the slope value, whatever the slope value initially is, that slope is decreasing, and eventually the slope here is 0. Of course, positive. You see, slope is positive, right? And it is 0 here. So slope is decreasing and eventually 0, and therefore one inverse of that slope is increasing. 1 by T is the slope, that is T is inverse of the slope, and therefore it is temperature is increasing, and eventually at this it is infinite, because 1 by slope is 0, so infinite. And in this regime is not very surprising to us because we are very familiar with this regime of temperature from 0 to infinity and 0 to very large. Okay. So what is happening physically? Now, suppose all the moments were in up or down in a particular direction, okay? All are in the same direction, okay? And then as you increase the temperature, they are thermally agitated and therefore changing their direction, and eventually at this point, all are randomly arranged, totally randomly arranged, right? So when they are totally randomly arranged, then you have the total entropy has a maximum value, and probably that will give you nk ln2 at this point. At this point. Now I am asking the question that in the discussion I have written, it is immediately apparent that the entropy will be 0 at energies plus n epsilon and also at minus n epsilon. Can you justify that?
আচ্ছা, এনার্জি যেটা বলছি, মানে এনার্জি যেটা বললেন যে প্লাস মাইনাস এন এপসাইলনে আছে, তো মানে সবটারই কি ওই মানে প্লাসেই থাকতে গেলে সবটারই প্লাসে থাকবে, আর না তোর নেগেটিভে থাকতে গেলে সবটারই নেগেটিভে থাকবে, এই জিনিসটা কি বলছেন?
না, আমি যেটা বলতে চাইছি যে এন্ট্রপিটা কেন 0 হচ্ছে when the energy of the system is n epsilon plus n epsilon or minus n epsilon.
স্যার তখন একটাই ডিস্ট্রিবিউশন সম্ভব হবে, ওই জন্য 0 হবে।
রাজেশ,
হ্যাঁ
অভিষেক, আচ্ছা সম্বিতা অনেকদিন কথা বলেনি। সম্বিতা, আর ইউ অ্যারাউন্ড?
হ্যাঁ স্যার বলুন।
হ্যাঁ, বলছি একটু উত্তরটা দিতে পারবে?
স্যার কোশ্চেনটা আরেকবার বলুন।
এই যে তুমি কোশ্চেনটা জিজ্ঞাসা করনি কেন, যে কোশ্চেনটা বুঝতে পারোনি? সেটা আমাকে জিজ্ঞাসা করতে হবে? I have to trigger you to ask the question. সম্বিতা?
হ্যাঁ স্যার বলুন।
No, sorry. Samita, you already replied. And Samashri?
স্যার বলবো কিছু আমি?
কে বলছে?
ইয়াজ স্যার।
Yes. Wait a minute.
আচ্ছা আচ্ছা।
Yes sir.
Can you make some comments on that?
থার্ড ল ওয়াইজ কি হচ্ছে মানে?
হ্যাঁ? Okay, not sure. Okay.
না স্যার।
Rajesh, mute. Rajesh, I have heard you. Okay. I heard your answer. And,
Yes, sir.
Yeah. So you can mute. I heard your answer. Yeah. I'll come back to you. Okay. Yajnobi, you are saying something.
স্যার মানে টোটাল পার্টিকেল সংখ্যা n যদি প্লাস n এপসাইলন হয় তাহলে টোটাল পার্টিকেলটাই আবার স্টেটে চলে যাচ্ছে, তাহলে একটা ডিস্ট্রিবিউশন সম্ভব হচ্ছে। আর যদি মাইনাস এপসাইলন n এপসাইলন হয় তাহলে টোটাল মানে সবকটা পার্টিকেলই ডাউন স্টেটে চলে আসছে, সেখানে একটা মানে পসিবল হচ্ছে, তার জন্য হচ্ছে এটা।
Okay. So Rajesh, Yajnobi basically repeated what you said. Right?
yes sir.
Okay. Absolutely correct. And since at when the energy is at minus n epsilon, then it is all up, because minus mu dot a, right? All up state, and therefore there is only one configuration. That is the only configuration. You exchange between them, it will not give anything new. All spins are say up, then if you exchange among themselves, it is not going to give any new configuration. And similarly, if you make all spins down at when the energy is n epsilon, then also there is only one configuration. It is not going to give any new configuration even if you interchange between the particles. And therefore at those states there is only one configuration, and therefore S, K, ln omega is 1, ln 1 is 0, right? and therefore the entropy is 0 at those energies. Is it clear, Shamasri, Sambita, and others?
Yes, sir.
Yes, sir.
Samita বুঝতে পারলে?
Yes, sir.
Yes, sir.
Shamasri বুঝতে পারলে?
Yes, sir.
Okay. All right. So, so this is the physics, okay? And now you see, now you come to this portion of the curve. Now, as you go beyond this, you see here the slope is zero, and it is, it is in the negative region, right? Because slope is negative in this side. So from here, if you go this way, eventually you will see that here it is slope is negative, but it is very small, pretty small. So that means that you have a negative infinite temperature, because once slope tends to 0, that means it is 1 by 0, means it is infinity, but the slope is negative, and therefore it is a negative temperature. Okay. Now, if you go down, so energy is increasing, your energy is increasing. Then go down, then you see that your T is always negative, and eventually come here, it becomes, you can denote it as T 0 negative, and it is 0 positive. Now, actually, suppose this temperature is T equals to 300, and suppose this temperature is minus 300 Kelvin, okay? Then this minus 300 Kelvin temperature is hotter than 300-degree temperature. Okay, so this portion is hotter than this because it has more energy. Okay, so at this moment it is kind of a theoretical concept from the nature of the statistics, entropy, and also from the relation of realization of temperature, the parameter temperature from the entropy, the way you can extract the temperature from entropy, then you understand that this temperature at this and temperature at this, we compare, this is hotter region compared to this. Okay, so if you bring two systems, and the temperature scale should be from 0 to plus 300 K, then plus infinity, then minus infinity, then minus 300 degree K, then 0 degree K, and minus, this should be minus 0 degree K. Now, for example, if the body with 300 degree Kelvin is brought into contact of minus 300 degree Kelvin body, then the equilibrium temperature should be, what should be the equilibrium temperature?
0 K.
No, it will merge there. It will be not 0, it will be plus minus infinity, because for them this is the kind of average point. This is 300 degree, this is minus 300 degree. So eventually it will merge there, not 0. So the concept again, it is not algebraic addition. As I said, minus 300 degree is hotter. It is beyond the infinite temperature. Okay, so it is beyond the plus infinity temperature. This is hotter than this. Okay, so then when you bring these two together, then they will equilibrate at this temperature. It's infinite. So this is the concept of negative temperature. And actually, there is an article and also experiment, how to realize negative temperature. So I will provide you with the article, and maybe you can, or maybe you can open the Patria's book, and there probably you will have the reference of that article. Okay, then you can go back to the article if you have interest. Then you can just simply go back and get that paper and you can read it, that how one can realize the negative temperature. That means if it was in some state, then you have to immediately, flip the states to get to reach, this place, okay, to reach to this place, this temperature. So I'll give you the article so you can read on this. So it is the same thing actually. I have repeated basically the kind of, this is the SK, K, then omega, and this side is entropy increasing positively, and this is for this entropy decreasing. So positive slope, negative slope, positive temperature, negative temperature, plus minus infinity here, 0 plus 0, 0 plus, 0 minus, and so on. But again, that's why I know that they will make a mistake the concept wise, and that's why I made this statement deliberately, that when you bring two objects together, one having temperature 300 K and one minus 300 K, minus 300 K means it's a concept, different concept, okay? It's not the concept that you're in the scale of thermometer, it goes down 300 degree Kelvin. It's not that, okay? It is the different concept. Then it will equilibrate at plus minus infinity. Okay, so this is the negative temperature concept, and in the next class, probably I will quickly go over the grand canonical ensemble, because I have already talked about the canonical ensemble, microcanonical ensemble, and canonical ensemble. As I have already, I have already spent lots of time on canonical ensemble. I think it will be kind of fair enough if I just quickly go through grand canonical ensemble, because lots of things are still remaining. At least I would like to cover the quantum statistics and also Fermi gas and Bose gas, even if not the non-equilibrium statistical or interacting statistical mechanics. So then let me stop here, and tomorrow you have the exam. So what time do you want to give the exam?
স্যার মানে আপনার কত মার্কের এক্সাম হবে বা কত টাইম হবে ওটাকে বললে একটু মানে ভালো হয়।
Maybe marking, so maybe I ask say couple of big questions. And marks, maybe I can give 20 and that can be given 40. That's not